Now that was coordinate system which allowed me to specify any point in space by with reference to a particular coordinate system by a set of numbers, by a set of 3 numbers. I was able to specify every point in space with respect to this coordinate system. Of course, I could have chosen any other coordinate system, but you know that if I choose a different coordinate system, the numbers associated with the points will change, but the points themselves will be physically the same. The points will not change, only the numbers that you associated will change if you change the coordinate system. Okay. Consider associating vectors to these coordinate systems. Now that we have talked about how to associate points in a 3-dimensional rectangular coordinate system, I want to now associate vectors on this plane, or I have to describe vectors on this space. So how do I describe vectors? Remember, all vectors are drawn with their origin sitting at the origin of the coordinate system, such that I can now specify any vector, the endpoint of any vector by 3 numbers. So in this particular case, I have a vector r, okay, which is called as the position vector, and this position vector has its origin at O and it is terminating at some point which is intersection of 3 planes. This plane that you are seeing in the front, which is slightly dark, is the x is equal to constant plane. This plane that you are seeing here is the y is equal to constant plane, and this plane that you are seeing here on the top is the z is equal to constant plane. So if you now bring all the 3 planes together, the intersection will be the point where the vector r terminates. So now I can draw a line from the origin until I reach the point here, and that will define a vector r to me. In other words, I can, given any vector whose origin is at the origin itself and which is terminating at any other point in the space, all I have to do is to set up the 3 planes so that I can describe the end point of the vector, okay. And this vector can now be specified by just 3 numbers, or I can resolve this vector into 3 different vectors. These 3 different vectors, how do I resolve that? Remember, resolving a vector means you take a vector and then you look at the components of the vector along x direction and along y direction. This is what we did for the 2-dimensional case. Now there is no reason why we cannot do this for the 3-dimensional case. So you take a vector, okay, and look at its component along the x direction, look at its component along the y direction, and look at its component along the z direction. So you can actually resolve any vector into x, y and z components, okay. So that is precisely what we are going to do, and when you resolve a vector, you will actually be generating 3 mutually perpendicular vectors, okay. Just as in the 2-dimensional case, you generated 2 mutually perpendicular vectors, here you are going to define, generate 3 mutually perpendicular vectors, okay. These vectors are x, x hat plus y, y hat plus z, z hat, where x, y and z without the hats are the magnitudes or the points that are dependent on the particular vector r that you are considering, and x hat, y hat and z hat are the unit vectors along x, y and z directions, okay. So this is the resolution of a vector. Now we want to add 2 vectors or subtract 2 vectors. We have already seen how to do this graphically, but with the knowledge of coordinate systems, is it possible for me to do all this without drawing lines every time and without translating one vector onto the other vector? Yes, it is possible, and to do that one you have to, so this is an example in which we are going to do that one. You have to start imagining that every point or every point can be represented by a vector, okay, whose origin is at the origin and which terminates at the desired point. For example, I have 2 vectors here, rp and rq, which are defining 2 positions. Position p, which is given by the coordinates 1, 2 and 3. How do I get to 1, 2 and 3? I move 1 unit along x, I move 2 units along y, and then I move 3 units along z, right. So I get to the point p, which is 1 unit along x, 2 units along y and 3 units along z. So this point is described equivalently by a vector rp. So please note that this point in space, which has its coordinates 1, 2, 3, can be equivalently defined by this vector rp, okay. Similarly, if I take another position q, which is at 2, -2 and 1, okay, I can define another vector rq whose origin again is situated at the origin of the coordinate system, and which is terminating or whose head is situated at 2, minus 2 and 1. Again 2 units along x, minus 2 units along y. So, you need to go to the left. So, minus 2 units along y and 1 unit along z. Now, you have a vector rpq, okay, which is a vector which is directed from point P to point Q. This vector is not defined in terms of the origin. How are we going to describe this vector rpq? Here is where the vector addition will come to my help. I know that this vector rp plus this vector rpq is equal to the vector rq. Okay. This vector rp plus the vector rpq is equal to the vector rq. What we said about all vectors being at the origin means that every position is is equivalently represented by a vector whose origin is at the origin of the coordinate system and which terminates at the particular point. However, the vector rpq is a vector which is not defined from the origin. It is actually defined between the 2 points P and Q, and you have to specify those points for this vector. However, you can specify the vector rpq in terms of the position vectors rp and rq. How do I do that one? You start from the vector addition that rp plus rpq is equal to rq, that is rp plus rpq is equal to rq, which implies that rpq is equal to rq minus rp. So, it is a simple transferring rp to the right hand side, you get rpq is equal to rq minus rp here. And I already know how to represent the vector rp. The vector rp can be represented, go back here, the vector r is represented by giving its 3 components x, y and z vectors, which are x, x hat, y, y hat and z, z hat. Therefore, rp can be written as x hat, 1 into x hat is just x hat plus 2 into y hat plus 3 into z hat. Similarly, rq vector will be 2 x hat minus 2 y hat plus 1 z hat. Now, if I subtract rq and rp, I am going to get rpq. How do I subtract that? In a given coordinate system, a vector is represented by 3 points x1, y1 and z1, or equivalently x1 x hat plus y1 y hat plus z1 z hat, and similarly vector b. The sum of the 2 vectors is given by the vector whose components are simply added like this. So, you have the x component added to get x1 plus x2, y component is y1 plus y2 and z component is z1 plus z2. Similarly, to get the difference between a and b vector, you have to subtract x2 from x1, y2 from y1 and z2 from z1. These 3 points define the end point of the difference vector a minus b. So, if you go back to the previous slide, rpq was a vector directed from p to q, and that was given by rq minus rp, and you can subtract the individual components, you are going to get a vector which is minus x hat minus 4 y hat minus 2 z hat. Equivalently, it can be represented as a vector with tail at 0 0 0 and head at minus 1 minus 4 and minus 2. Okay. This is how you are going to subtract the 2 vectors. So, we have seen how to define a vector in a 3-dimensional Cartesian coordinate system. So, given a vector A, we can resolve this vector into 3 vectors which are mutually perpendicular. So, when we say mutually perpendicular, we mean by if you take pairs of vectors, these pairs of vectors will be perpendicular with each other. So, this vector A can be resolved into 3 vectors Ax x hat plus Ay y hat plus Az z hat, and we call this Ax, Ay and Az as the x component of the vector A, y component of the vector A and z component of the vector A, and the vector that we form along the x direction will be the component times the vector. Now, one of the things that we have seen in Coulomb's law is that we not only require the vector, but we also require its magnitude, because the magnitude gives you the separation between the 2 charges. So, when you have 2 charges separated by a distance r, we define a unit vector along the line that joins the 2 charges, but at the same time I also want to know what is the magnitude of the separation. To get the magnitude of the separation, we need to define the magnitude of a vector. We normally denote the magnitude of a vector by putting it in between 2 vertical lines. Okay. So, this denotes the magnitude of a vector. Sometimes you simply write down the number without a vector notation, that would also denote the magnitude of a vector, and this magnitude of a vector is given by square root of ax square plus ay square plus az square, which you can think of as a 3-dimensional generalization of Pythagoras rule. Okay. So, magnitude of a vector actually tells you the distance of the vector from the origin. That means, at what point the head of the vector is located with respect to the origin. So, the distance from the origin of the vector to the tail point or the end point of the vector is the magnitude of the vector. Okay. What is the magnitude of a unit vector? 1. Okay. So, do not forget that. How do I define a unit vector along a particular direction? So, I have a vector A which is starting with the origin O and terminating at some point in the 3-dimensional space. How do I define a unit vector along that? What is a unit vector? It is a vector which is directed at a particular direction, any direction. If the vector is directed along x direction, then it will be a unit vector x hat. If it is directed along y, it would be a unit vector along y hat. Now, if I have a unit vector directed in general along A, I can denote this as some A hat, and what is that? It is a vector. So, I need to give the vector A itself, but since the magnitude of the vector has to be unit, I will have to divide this A by its magnitude. It is some sort of normalization. Okay. So, if I have 10 x hat as the vector along x direction, and if I divide the 10 x hat by 10, which is the magnitude along x, I will get x hat, which is the unit vector along x. So, the same rule, if I want to specify a unit vector A, I specify this by writing A and putting a hat on top of it. I can sometimes use bold letter A with a subscript A, or I can use UA, all these different notations you will be seeing in literature. So, a unit vector along a particular direction is given by the vector divided by its magnitude. This is the unit vector along a vector A in its particular chosen coordinate system. Okay. Here are some exercises for you. I have given you 3 points. So, one point is M at -1, 2 and 1, and a point N at 3, -3 and 0, and another point P which is -2, -3 and -4. What I would like you to do is to first find a piece of paper and draw the 3 axes and try to represent these points M, N and P on that piece of paper. Okay. So, I want you to get some familiarity with representing the points. So, take this as an exercise and locate the points M, N and P. Now, remember, to every point M, N or P, I can actually define a vector whose origin is at the origin and with whose head is at M, N or P. Okay. I want you to find out this vector R M N. What is this vector R M N? It is a vector which is directed from M to N. Okay. And what is that vector given as? R N minus R M. This is in general. If I have a vector R I F, okay, it would be a vector which is directed from the initial point to the final point F, and then that vector will be given by the position vector R F minus position vector R I. Okay. So, R M N I want you to find out. Similarly, I want you to find out R M P and then add to this R M P to R M N. You need to do this both graphically as well as using the coordinate system values. Okay. Finally, find the magnitude of the vector M, also find the unit vector along the direction M. Okay. How do I find the unit vector along the direction M? You know what is the vector M and divide by its magnitude. And what is the magnitude? You have already found that out in the previous exercise. Okay. So, you do all these exercise to gain some familiarity with using the vectors. Okay. So, we have taken a large digression from Coulomb's law. We were discussing Coulomb's law, and then we started discussing vector analysis, went to coordinate systems. All this was required because electromagnetics is essentially a 3-dimensional subject. Okay. You need to know vector analysis, you need to know how to set up coordinate systems if you want to have good success in electromagnetics courses. Okay. So, we will now come back to Coulomb's law and try to work out a problem. Hopefully, whatever that we have learnt in the vector analysis and coordinate systems will come to our help and help us find the vector, will help us find the solution to this particular problem. What is the problem? It is essentially a simple problem. We have an origin, okay, and we have 2 charges, one charge at Q1, the other charge is at Q2. The charge Q1 is 200 microcoulombs, okay, micro is a sub prefix which means that 10 to the power minus 6. Okay. So, this is 200 into 10 to the power minus 6 coulombs or 200 microcoulombs, and this Q1 is located at point 103. See, you can go 1 unit along x. So, here in this particular figure I have rotated the axis to show you everything, hopefully in a clarified manner. This is the x axis, this is the y axis, and this height is the z axis. So, to locate point 103 I have to move 1 unit along x, there is no movement along y. So, y is equal to 0. Now, I have to move along z to z is equal to 3 to reach point q1 or charge q1, whose value is 200 microcoulomb. Please note that this is a positively charged charge which I have put, positively charged particle which I have put here. Okay. Similarly, we have a charge q2 with a value of 30 microcoulombs. Okay. It is also positively charged and it is located at 0 to 1. So, 0 means x is equal to 0. So, you are now looking only at the intersection of y and z planes, that is the point 0 to 1 is in the yz plane. Okay. So, you can see here that I have to move 2 units to y and 1 unit to z in order to reach point q2. Now, the question is q1 is exerting some force on q2, find the force at q2. Okay. So, Coulomb's law will help us find this, but Coulomb's law requires us to give both magnitude as well as direction. Magnitude is the easier part, okay. Direction is something that we want to understand. If I denote the point where the charge q1 is placed by a vector r1, and if I denote the point where the charge q2 is placed by a vector r2, then I know that because Coulomb's law also tells me that the force will act along the line that joins the two charges q1 and q2, right. It acts along the line that joins the charges q1 and q2. I define r12 as a vector which is starting at q1 and ending at q2. Okay. In this direction is the force F2. Okay. So, I have r1 position vector for charge q1, r2 as the position vector for charge q2, and r12 is a vector starting from q1 to q2. And I know clearly that r12 is given by r2 minus r1, where r2 is the position vector of this charge of charge q2, r1 is the position vector of charge q1. Why? Because remember RIF, I is the initial point, F is the final point. So, the vector that would be described by RIF is actually given by the position vector of F minus position vector of I. So, RF minus RI. Okay. So, what is R1? R1 is the point which corresponds to charge q1, which is 103. This is in the x z plane. So, you can see that this is how x will increase, this is how z will increase. So, this plane is the x z plane. Okay. And in this x z plane, R1 is given by x hat plus 3 z hat. Similarly, R2 is in the y and z plane. Okay. So, R2 is given by 2 y hat plus z hat, and R12 is given by R2 minus R1. Remember how to do R2 minus R1? I have to look at the components, the y component of R2, subtract the y component of R1 from the y component of R2, subtract the z component of R1 with z component of R2, subtract the x component of R1 with x component of R2. Okay. You can do this subtraction and you will see that R12 is a vector that is in the 3-dimensional, it has all the 3 non-zero components. It is given by minus 1 x hat plus 2 y hat minus 2 z hat. This minus 1 is just for convenience I have written. This is minus x hat plus 2 y hat minus 2 z hat, and that is this vector R12. Now, force acts along the line is fine, but what we want is not the force acting along that one. What I want is not the statement that force is acting along the line R12. What I want is a unit vector along the line R12. What is the unit vector along line R12? That will be the vector R12 divided by its magnitude. I have already found out what is R12. The magnitude of the vector R12 is its x component square plus y component square plus z component square, all under root. Okay. And if you do that one, you will get minus 1 square plus 2 square plus minus 2 square, which will be 3. So, the unit vector along R12, that is along this vector R12, is 1 by 3 minus x hat plus 2 y hat minus 2 z hat. I hope that you derive this one for yourself and convince yourself that this is correct. Okay. So, coming back to the force part, I have already found out the unit vector. So, now I know that if I take the magnitude of the force and then multiply it by the unit vector along the line R12, I will get the full vector force F2, right, a vector force F2 I will get. What is the magnitude of the vector force F2? The magnitude of the vector is 1 by 4 pi epsilon 0 R12 square. Why epsilon 0? Because there was no specification on the medium, so you just take the medium to be air or free space, and we know that for air or free space epsilon r is equal to 1. So I have 1 by 4 pi epsilon 0 R12 square. Now here is an approximation that you can use frequently. 1 by 4 pi epsilon naught can be approximated as 9 into 10 to the power 9, because epsilon naught is in the order of 10 to the power minus 12, okay, and when you multiply 4 pi and the corresponding value for epsilon naught, this is an approximate value for 1 by 4 pi epsilon 0. You can put that approximation. If you have a good calculator, you do not have to do this approximation, but if you decide to do this approximation, you can just write it over here, multiply the magnitude of the charges. Remember, the force on a charge Q2 is proportional to the product of the charges, charge magnitude Q1 and Q2, as well as and inversely proportional to the square of the distance between the two. Okay, the distance between the two is 3 square. Okay, that is R12 square. So you are going to get 6 newtons. Okay, this is the magnitude of the force. However, in terms of the vector, I need to multiply the magnitude by the unit vector. So this is the unit vector in brackets, and I am multiplying that by the magnitude. So this is the force F2 that is acting on charge Q2 because of charge Q1. Now that you have seen this example, re-look at the example once more, understand all the steps that are there in this example, and then try your hand at finding the force exerted by a charge Q1 which is placed at the origin of a 3-dimensional coordinate system 0, 0, 0 and has a value of 100 nanocoulombs on charge Q2 which is placed at 4, 3 and 0 and with a value of 3 nanocoulombs, and you can verify that the answer is approximately 86.4 x hat plus 64.8 y hat nanonewtons. It is a very small value because the charge magnitudes are also quite small and the distance between the two charges are quite large. Okay. Now before leaving this exercise, you ask yourself one question: does it make sense? Does this answer make sense? Well, the answer makes sense because look at where the charge Q1 is placed. It is at origin 0, 0, 0. Okay. Now charge Q2 is placed in xy plane only. It is placed at 4 and 3. Its z component is 0. So the force that must be acting on Q2 must originate from that origin, because the Q1 charge is at the origin and will be directed to Q2, and this force will only be in the xy plane. There is no chance for the force to be in the z plane for this problem. Okay. So in this problem you expect only the x and y components for the solution, and that makes sense. Okay. You have to always do a sanity check on whatever the answers that you find, so that you are seeing that everything what you have done is correct. So this sanity check, if you keep doing it, you will not make mistakes while deriving the answer. Okay. I want to now introduce Coulomb's law and change the notation that we use slightly. So previously we had used AR12 or AR as the unit vector, but when we go to different charge distributions, it becomes easier to use a different notation. There is a reason why we go to other different notation. I will tell you when we go to that notation later. We keep some source charges. Okay. These charges I am still labeling them as Q1, but I am also specifying the position of the source charge. Okay. The source charge Q1 is at position r prime. R prime is a position vector from the origin to the source point, and the test point, okay, previously what we considered as charge Q2, which is defined by the position vector r, is what I am calling as the test charge. Okay. So this is known as the source point. This r without any prime is known as the field point. This is the point where I am interested in finding the force. Okay. You will soon see why this is called field points, but for now just take the fact that the position vectors without a prime are called as field points, position vectors with prime are called source points. Okay. So this part has not changed. All that we have done is to identify the position of the charges. So Q1 is at r prime, Q2 is at r. What is the unit vector? Unit vector is the one that joins r prime and r. So it is a vector that is directed from r prime, that is from the source point to the field point, and we know that that vector is given by r minus r prime divided by its magnitude. Okay. The magnitude of a vector is r minus r prime magnitude. The separation between the two vectors is magnitude square. The magnitude square part will make r minus r prime square, that gets multiplied by r minus r prime, so as to give you r minus r prime cube. Okay. So, keep this in mind. Now, you will frequently find, as we go to the next lecture, you will frequently find that you are not dealing with only one point charge or dealing with one charge distribution located at a particular point in space. You will be dealing with many charges or a continuous distribution of the charge. So, for that case we have to know how to obtain the force when you have more than one charge. So, let us say I have 10 different charges, how do I obtain the force? The answer comes in the form of superposition of forces. What is this superposition of the forces? Fix the test charge location and do not change that one. So, let the test charge be located at the position r, and we will call that as Qt. Just that subscript of t indicates to you that this is a test charge. So, I have Qt of r standing for the position vector of the field point where I am keeping the test charge. Now, the source charges could be placed anywhere. This placing of the charges anywhere, I am denoting this by r j prime, where j corresponds to the jth charge of magnitude qj or signed charge magnitude qj, and what I want to find out is the force experienced by the test charge, and this force will be given by the vector sum of, this is vector sum, this is not a scalar addition, this is a vector sum because individual forces are vectors. What does this F1t mean? It is the force because of the first charge on the test charge. Force F2t is the force of the second charge, second source charge on the test charge, and so on. And how are these forces obtained? You simply break up the charge, or you simply find out the force because of each of these source charges and then sum together, and summing is happening only on the source charge distribution. Okay, that is why this summation sign with a j is applied to the source charge, not to the field point. So, in fact, you can pull this field point outside, and whatever that you are left with when you multiply it by Qt of r is going to give you the force by the jth charge on the test charge Qt. Okay. So, this is the force on the jth charge of the jth charge on the test charge, and if you sum all these forces, you are going to get this particular expression. Okay. We will not solve any problem with superposition of forces. We will in fact solve a slightly different problem of continuous charge distribution later. Here is where I want to talk about line, surface and volume elements and kind of finish this Cartesian coordinate system. For now, we will be requiring only Cartesian coordinate system. Suppose I have a two-dimensional plane, a two-dimensional coordinate system. This is the x axis. Think of the green board here or a black board in your class as an example of a plane. We have x axis and perpendicular line which is y axis. The point where these two meet is the origin O. Now, if I move a certain distance, say dx, along the x axis, I will actually be generating a vector whose head or whose tail or the origin lies at 0 and whose head lies at dx. That is, this particular vector that I have generated by moving along x direction is dx x hat. I could now move vertically to generate another vector which is dy y hat. Of course, this dy y hat is actually parallelly translated from this particular vector, right. So, you need to remember that one. Okay. This vectors that I have generated are called as the line elements. This is called as the line element along x direction, and this line element along x direction is given by the distance that I have moved along x axis. Similarly, I have the line element along y, which is the distance I have moved along the y axis. This is dy y hat. Okay. If I now consider a general direction of movement, I can write down this as some dl, okay, and this vector dl, which represents the vector from the origin to this particular point, call this as point P, okay, can be now decomposed into two components, dlx plus dly, which is nothing but dx x hat plus dy y hat. What is the magnitude of this dl vector? the magnitude is dx square plus dy square under root, right. The magnitude of the dl vector is dx square plus dy square under root. Okay. These are called as line elements. You will be seeing line elements and line integrals very soon. So, this is the simplest line element that we have considered. Okay. Now, we will consider surface elements. For this, I will be going from 2 dimension to 3 dimension, because with 2 dimensions I can only define one surface area. With 3 dimensions I can actually define 3 surface areas. Okay. So, in accordance with the right hand rule, I have this as the x axis, this as the y axis, and this becomes my z axis. You can imagine that this is a object that I am considering. The line that you are seeing along this one will be the x axis, or maybe we can consider this way. The line that you are seeing here along this is the x axis, this would be the y axis, and if you move from x to y, you are going to see the direction along z axis. Okay. Now, if I ask you what is the area of this particular face, the face that you are seeing, what is the area of this face? To get the area of a face, I need to know its length and width. What is this length? Some length, let us say, but this, if I am assuming that all these lengths are some dy, dx and dz, so the face has an area of dy. So, as you move along y, you have dy and then dz, right. So, if I move a distance of dz in this direction along z, and if I move a distance of dy, I will get the area dy dz, that would be the area dy dz. So, I have an area which is dsx, I will call this as dy dz. This is the front surface area, okay, in which I have moved dy and I have moved dz. Now, I want to associate a vector to this face. How do I associate a vector to this face? I will simply multiply this by a vector x. How is vector x pointing? Vector x is pointing away from the surface, right. In fact, this vector is perpendicular to this surface area. So, this is how we associate a vector surface area. Okay. We associate a vector surface area by giving the area and then considering a direction that is perpendicular to that area, or in mathematical language we call this as normal to this surface area. So, this vector x is normal to yz, the surface area dy dz. So, this is the vector surface area along x. Similarly, if I go dx and then move dy along this one, I am going to get the area of this top surface or the bottom surface. Okay. I will call that as dsz and say this is dx, dy and z direction. Of course, I could have chosen the direction of x for the front surface to be going inside, which would be opposite to the x direction, but we always use the surface areas again as similar to the Cartesian, the right handed rule. Okay. The right handed rule tells you that you go from x to y, you will move along z. Similarly, dsx will be dy dz and you move along positive x direction. So, dsz will be a vector surface area of this top surface or the bottom surface pointing along the z direction. Okay. So, this particular bottom surface or the top surface is by dsz. Here it would be pointing along z direction, here it would be pointing along x direction. Now, can you figure out what would be the area, vector area for the sides? Yes, you can easily figure this out. This would be dsy and dsy will be dx. So, you move along like this dx and then you move dz. Okay. So, it would be dx dz along y direction. Okay. So, these are the 3 surface elements or surface areas that you are going to see. This is the magnitude of the surface area, and this is a vector that would be perpendicular to the plane that contains these 2 elements. Okay, dy is the direction along y, dz is the direction along z in which you have moved or distances that you have moved, and a vector surface area will be something that would be perpendicular to the two. Okay. What would be the volume element? That is, what is the differential volume of this box? Well, you have length, you have width, and then you have height. So this is nothing but dx, dy, dz. Is there a area associated with that? Thankfully no. So the volume element is a scalar which is dx, dy and dz, and gives you the area of this particular cuboid. Okay.